So, in the single variable in the 2D world, we use chain rule for cases where we had f. So if you had f as a function of x, and then you have x as a function of t, and if you wanted to find, well, I know how f changes as x changes. Well, how does f change as t changes? Well, to do this, you just use a chain rule. You take the derivative of both sides, and I get f prime of. No, I shouldn't use that notation because that's just not true. I get df dt. It will equal. You would do the derivative of this thing, so this would be df dx, right? You take it with respect to x, and then you multiply with respect to, well, you do like dx dt, right? And this reasoning is that, well, hey, the dx's kind of cancel out, so you're left with df dt. But more rigorously, you would think about, well, when you're doing chain rule, you're really going to do f prime of x, right? You take the derivative of the outer function with respect to the inner function, multiplied by x prime of t, right? So it's just chain rule. It's just chain rule. And we can do chain rule in the 3D world, kind of. We don't really come to this conclusion like so. Let's say we have a function, so I guess I should just use, let's say I have a function z equals, like it's a function of f, x, and y, right? It's some sort of function of x and y, and then I know x and y are functions of t. Well, what you find is that the rate of change of z with respect to time will end up equaling, and this is kind of the chain rule formula for case one. Case one being where x and y are just single variable functions. You get partial z partial x times dx dt plus partial z partial y dy dt. And there are kind of two ways to think about why this works. The first way is using differentials. We know in differentials, right, the differential dz will end up equaling partial z partial x dx plus partial z partial y dy. And we talked about how this differential dz kind of represents the change in z for a given change in x and y, but specifically when those changes of x and y approach 0, you get the differential. Now, right, so this is like the change in z for very, very small changes in x and y. Well, this is not rigorous at all, but just one way to think about it is, well, if you divide everything by dt, you're essentially looking at, well, how does the differential dz, right? How do those very small changes in z change over very small like changes in a certain variable such as t, some other variable that x and y depends on. And you can see we get the chain rule formula. Now, another way to think about it is, in terms of rates, right? You're saying, hey, kind of like, right, dz dt, right, this rate dz dt will equal, right, if you look at this partial x and this dx, I know they're not the same thing, and they're really not, and once again, this is not like a rigorous proof, but they kind of cancel out, and you get this rate, partial z over, dt, which is rate 1, and you have to add that rate to this rate, right? When the dy's cancel, you get partial z over dt. That's the second rate, so the total rate will end up equaling the sum of those, dz dt. That's another way to kind of think about it. In all honesty, the book, I know this is called the chain rule. The book doesn't really, like, the proof it gives is not a chain rule proof. You know what I mean? So why is it called chain rule? I guess it's resembling of chain rule. I'm not entirely sure. It's resembling, like, maybe it was resembling the 2D chain rule. Maybe that's why, but I don't know. Point is this is a really useful formula for when we have things like, when we have, a function depending on two variables which both depend on another variable. So let's do an example. The example I'm going to do is, let's say z is equal to sine let's do, I'm trying to remember. Let's do 5t to the 4th plus, or no, let's do sine, what am I doing? I just kind of gave it away. Not give it away, but sine x minus y. And then let me, x minus, or no, let's do, okay, let's change it up. Okay. So we can have z equals cosine x plus 4y. And let's say x is equal to 5t to the 4th, while y is equal to 1 over t. And, you know, you could technically, you know, plug these both in, but let's say we want to use a chain rule, right? Let's say we, you know, it's a Calc 3 test, we want to use Calc 3 concepts. How do we go about finding dz dt? Well, we just use a formula. So let's go ahead and find, first of all, let's find all our partials that we need. So partial z, partial x. Right, x is like, we treat the 4y as a constant, so really we're doing negative sine x plus 4y times the derivative of the inside, which we just, you know, derivative of x plus 4y, it's just x, or it's just their derivative of x, which is 1. And then if we do partial z, partial y, same idea, negative sine x plus 4, but now the derivative of the inner function, right, we're taking it with respect to y, it's going to be 4. So times negative 4y. Basically negative 4 sine x plus 4y. Now we take these derivatives, right? So dx dt, well, this is just power rule, 20t to the 3rd. And then for the derivative of 1 over t, this is negative 1 over t squared. And you can do this, you can show this using, you know, if you're really taking the derivative of t over negative 1, you do power rule, put the negative 1 in front, and then subtract 1, you get negative 2, which in turn just becomes negative 1 over t squared. Now, the final rate, we can just build pretty quickly. dz dt will equal, so we're going to do partial z, partial x, which we found is negative sine x plus 4y, negative x plus 4y, and then we can times dx dt, which is 20t to the 3rd, plus partial z, partial y, which is negative 4 sine x plus 4y multiplied by dy dt, negative 1 over t squared, the negatives drop, and then I get a final answer. And I can simplify this. I can, like, you know, what I would recommend is on a test, put in the substitute in x and y into here. Reason being is because then you're getting, like, it's a function of time. You know what I mean? It's not really a function of x and y. You can just substitute in 5t to the 4th and 1 over t for all the x's and y's, and boom, it's going to be a pure function of time. Now, let's talk about the second case of the chain rule, where, hey, maybe now we have x and y depend on, like, they're also their own multivariable functions. So let's say s and t. I think that's what the book uses, s and t. It's a very similar idea, but now we have to do partial z, partial z, partial s, and partial z, partial t. Because in the last case, x and y both depended on time, which means really the rates only depend on one variable. You know what I mean? Because if you were, you know, in the case where they both depended on time, it was actually really just a one-dimensional function, x of t, y of t. Well, both x and y depend on a single variable time. This is just a single variable function. So we just had dz dt, but now they depend on two variables, right? X and y depend on s and t. So now the rates will also depend on two different variables, and now they're going to be partial derivatives because of that. So it's very similar though. We're going to have partial z, partial x times partial x, partial s, plus partial z, partial y, times partial y partial s, right? Very similar. It's just now your variables have changed. Instead of doing dx dt, I'm doing partial x partial s, because that's, it's now with respect to s instead of t. But in this case, it's going to be very similar because it is in terms of t. So partial z partial x times partial x partial t plus partial z partial y times partial y partial t. Okay, so this is case 2 of chain, where if it depends on your thingies depend on multiple variables. Why did I say it like that? Why am I saying thingies? This is case 2 of chain rule, where your x and y, right, for your original function depend on 2 variables. So let's do an example. Let's do this example. So let's say z is equal to arc sine x minus y, where x is a function of, or we don't even need this notation, I guess. I guess it doesn't really matter. S squared plus t squared, and then y is going to equal 1 minus st. And I want to find both partial z and partial s. Just for time's sake, I'm going to only find partial z partial s. I'm going to leave partial z partial t up to you guys. And if you find a solution, just comment and I'll give you the answer so you can check how you did. But the way we're gonna do this is just using the case, right? This is not a crazy idea. We use the formula, which hopefully is kind of intuitive, and then we go from there. So let's find all our partials that we need. We need partial z partial x. So let's go ahead and do that. Partial z partial x. I'm working with the z function here, and it's an arc sine. So the derivative of arc sine is 1 over root 1 minus, and then whatever your input is. So 1 minus the input, x minus y, squared. And that's hopefully a derivative you remember from Calc 1. Let's multiply by the derivative of the inside, which is pretty nice. Derivative of x minus y with respect to x is just 1, right? Because y is a constant, and then x derivative of that is just 1. So now we don't have to multiply by anything. Well, we do, but we're multiplying by 1. Because it's chain rule. So partial z partial y, very similar, 1 over root 1 minus x minus y squared. The derivative of the inside now, though, is negative 1, because now we're differentiating x minus y with respect to y, and the derivative in this case would be negative 1, because of that negative sign there. So I get negative. There you go. So now, I don't know why I sound tired. We want to find partial x. We want to find partial z partial s. So we need to take our partials with respect to s over here. So partial x partial x partial s. The t squared is just a constant, so I just get 2s, and then partial y partial s. The 1's a constant, that goes away, and t is treated like a constant. So if we're differentiating with respect to s, the derivative would end up being negative t. Excuse me. Wow. Okay. So what we can do now is build up our little formula here. So I have partial z partial s, which will equal 1 over root 1 minus x minus y squared multiplied by 2s, right? I'm doing partial z partial x multiplied by partial x partial s plus, and I'm going to do plus here because this, I know I'm taking this negative multiplying by negative. I get 1 over root 1 minus x minus y squared times t. So the negative t and the negative 1 here, the negatives both cross off. And this will end up being a fraction with a common denominator. So I can actually just put them both, right? I can combine this fraction. I get 1 minus x minus y squared, 2s. Oh, I'm writing d's. I'm sorry. It's a habit that I need to break. Partial z partial s, 2s plus t. So there you go. That is chain rule. Try partial z partial t as a way to check your understanding, and then comment below. I can give you the solution if you need it. But yeah, thank you for watching. Hopefully this made sense and wasn't that crazy of an idea. I think this is kind of just like an application of what we've been learning so far.